Bon dia a tothom, soc el Ferran Marquès, el director de l'Escola de Telecomunicacions. Tenia una idea en ment de com presentar això. May I switch to English? Let me switch to English. I had an idea of how to present that, but I have to change. I have to change because it's one of the most crowded events I have ever seen here. So I think that we have done something right. With Jordi, when we saw the possibility of bringing Uriol and Joan here to give these talks, we thought it could be a good idea. And we were not aware of how good the idea was. We had one initial clue was that Jordi presented some months ago a book about TensorFlow, and it was as crowded, not that much, maybe not that much, but very crowded as well. So I think that the concept that we are today going to discuss is very relevant, and the two persons that we have brought are very welcome here. Let me then move to the two people. We are extremely happy. I was discussing yesterday by email with Miguel Angel Raja, the director of the FIS, about how to present them, and we were concluding, let's celebrate they are here. Period. I mean, we have two people here which are former students of our school, and it's our pleasure to allow them or to welcome them here. And okay, my turn is to present Joan, and Miguel Angel will present Uriol, and that was just by clicking a coin, so no other thing behind that. I don't know if you have had time to read the short video of our two speakers, but let me go very fast. Joan Joan Bruna is a former student of his school. He's a former thesis. He has the double degree with mathematics and telecommunications, electrical engineering. Okay, and as far as I know, both with honors. Then he moved to Paris. He studied in Cachan. And I think that it was a master's degree you performed there. Okay. After the master's degree in Cachan, I don't know if you know, Cachan is one of the most reputed schools in mathematics, at least, in Europe. And then he moved to a company, to a startup, and he was working on image processing. And then he started, or at the same time, he started the thesis. Correct?
Yeah, okay. Correct.
With Stéphane Bala.
Yeah.
In the Polytechnique in Paris. Okay, from there, he moved to the New York University, so he was a period over there, and then he started working on Facebook. This is the part I didn't know about. And then he was working with Facebook, okay? And nowadays, in 1 year and a half, more or less, he is at Berkeley. So I have said quite a few big names in all our area, and all of them related to Joan Bruna. So I think that it's really nice to have him here. Okay, I stop there and pass the phone to him. Okay, please.
Okay. Okay. Thanks a lot, Ferran, for the introduction, and gràcies a tots els que esteu aquí també, és veritat que tornar a l'escola on vaig estudiar sempre és alguna mica especial i només crec que he de dir el primer cop que torno aquí a parlar. And so that's about everything I have to say in Catalan. So first, thanks all the English speakers, because you really made my life much easier. I mean, I would never have been able to give this talk in Catalan. So thanks for being here. Okay, so let's go to it. So that's my talk. That's the title of my talk. So as you see here, there's a very fancy name, Convolutional Neural Networks. If you have been following, even I think El País or La Vanguardia, BBC, they talk about deep learning a lot, so convolutional neural networks, maybe it's one of the keywords. And then there's another word that is a bit more, maybe less fancy, but still very important. And so what I'll try to do is to combine this, try to make a bridge between what people hear, maybe not that mathematical, with maybe deep, more important key mathematical questions. So let's start. So another thing that you have heard in many general media, we are in the area of big data, data analysis, the load of data. But the fact is that images are big. Images, we have a lot of them. But we have been working with images for a long time. I mean, mathematicians have been caring about problems involving images for, I don't know, 30, 40 years, as far as I know. And one of the first talks, so one of the first things that we can try to do is to try to, let's simplify things, and let's try to put, signal processing in a sort of one-dimensional line. Okay, so let's start almost like historically. Okay, so one thing that you might want to do with images is, okay, let's try to compress them, right? Let's try to take an image that is 1,000,000 pixels, and let's try to make it squeeze into as few pixels as we can. Or maybe we have images and we add noise to them, and then we are trying to ask the question, how to remove the noise from these images. So these questions, actually, we have a very good picture of how to do them. Okay, so we understood pretty well how to solve these questions. And the tools to solve these questions are essentially functional analysis, harmonic analysis. Okay, so we know that we can take an image. Sorry about the contrast here, it's not very good. But here you should see a lot of black. Here you should see a lot of wavelet coefficients that are very small. And so these are ideas that really change the way we think about images, right? So we understand how to do this problem. But now we can make the task a little bit more complicated. Okay, so now this is another problem. Sorry again for the quality. So here what you should see is a very crappy, low-dimensional, noisy image. And here the goal of the game is to go from something that is ugly to something that is crisp and high resolution. Okay, so that's an inverse problem. So that's yet another, you can say that it's a bit more complicated than denoising. How do you do that? You have to mix maybe some properties of images, but maybe you have to do something else. Okay, then we can make the task even a bit harder. Okay, so now the goal of the game is I give you images like this. So these are, I think, house signs. Google have done a great job collecting this data set. So here the goal of the game is you have your Google car. He drives about the streets, and then he takes pictures. And so, of course, we want to map pictures to some data that we can interpret. So we have to try to understand, to infer, what is the class of this image. And here, these pictures show, okay. So these pictures show numbers, and there are different conditions, right? Different light, different color, different point of view. A very famous data set in machine learning is the MNIST. Okay, so here we have handwritten digits. The goal of the game is to read checks. Okay, so we need to infer what is the digit class here. And people have different writing styles. Okay, so we need to be able to infer, to extract this information under a variety of different conditions, right? The different handwriting styles. Speech recognition. So I don't know if here you have people working on speech recognition. I think that you were working, so maybe you might know what this word is. Maybe not. Okay, so you are not that expert. Okay, so this is encyclopedias. Okay, so that's a word, encyclopedias. That's a man. That's a woman. Okay, for us it's really the same word. But when you look at the low level, okay, that's a signal. That's a time frequency representation of this word. How can you make this thing look the same? How can you infer that there's the same word? If this is not hard enough, let's make it harder. Okay, so now that's image recognition. So here you have not just 10 digits, or not just 10 numbers, or not just like, 40 phonemes. You have objects in the wild. Okay, you have 1,000 classes here. That's a data set that we'll talk about it later. It really changed the way we do computer vision. So here you have a huge data set with very complicated structures. Not only we have to be aware that you have objects that can be taken under different lighting, different pose, different orientations, but you have something that is much harder to grasp mathematically. Okay, so you have here, a street or a cab. There's a huge variety, right? There's really a huge diversity of orientations, aspects that a same class can have. Okay, so that's a really, really super complicated. I put it very far in this axis. So if this is not hard enough, Uriol here came up with even harder task. Okay, so that's the task that is completely crazy. That I give you an image, and the algorithm has to come up with a caption, automatically caption. Okay, so that's something that Uriol managed to do. Put a picture, and Uriol came up with 2 pizzas sitting on the top of the stove. Okay, so how can you combine? So remember, here it's completely crazy. You have pixels. Okay, you have 1,000,000 pixels, and somehow you have to figure out how to abstract that here is a pizza, how to abstract that you have not 1 pizza but 2, and how to abstract that there's an oven and that there's this semantic relationship. Okay, and all that producing a sentence. Even harder, playing Go. Playing Go, how do you do that? If before we had low-level properties from images, now we have to be able to abstract this thing and apply it in a game that has completely different rules, completely different low-level structure. But still, what we will see, and maybe Oriol is going to tell us a little bit about it, just maybe 10 seconds, sorry about that. Actually, I'm doing advertising for Oriol, so he doesn't have to do it. I think that that's much better taste. Okay, so this is actually something that was done at DeepMind, which is where Oriol is working now. And that was, probably you heard about it in the general media. That was considered one of the landmarks in AI this year. Okay, so the tools that we are going to describe, the mathematical tools that we're going to talk about, they can be straightforwardly applied to this problem. It can get even more crazy. Image modeling. Okay, not only I have images and I want to understand things about these images, we can also ask the other question. Can I have an algorithm that creates images, that's the painting for us? The answer is that, again, the same mathematical questions that will sort of bring us towards this right of the axis, we can crush them and we can apply them to this problem. Okay, and this year we had fantastic papers. You can take 2 bedrooms and you can interpolate between bedrooms. Okay, so you are not just taking interpolation as we learn it from Ferran's class, doing a linear interpolation. You can interpolate bedrooms and you get bedrooms all the way. How can you do that? So all these things just sort of try to, it's like a mindset, okay? So we have the same images are somewhere, always here along this axis. We have different questions, different tasks that we ask on these images. And we need to have I have like a mathematical background. So we need a scheme. We need a way to think about these problems in a somehow unified way. Okay, and so the way we are going to use what we are going to try to do to think about these tasks as a whole is to, in a sense, come up with a notion of similarity. Okay, so here we have images, but every task requires a different way to compare images, right? To treat them together. Okay, so in this part of these tasks, this distance here is something that is very close to what mathematicians told us about. Okay, so just basically doing a linear transform, like having a very well-designed linear transformation, and basically working on the Euclidean space defined by this linear transformation. Okay, perhaps exploring some sparsity structure. But as we move along this axis, we will need to really change the notion of similarity in a very drastic way. And the way we are going to do it is that we are going to try to define a representation, okay, a feature extraction, that is going to define a similarity that is going to be appropriate for each task. Okay? And as we move along this axis, how much learning do we need to infuse into the problem? Okay? How much can we impose a priori? How much do we need to learn from the data? That's one of the questions that we are going to try to answer today. Okay, that's for data. The other very important key concept that I'm going to talk about in this talk is this notion of course of dimensionality. Okay, so what is the course of dimensionality? So these things that I talked about involve images. Okay, images, you can abstract images as being a point, a vector in a super high dimensional space. Every coordinate in that space is a pixel. How many pixels do I have? Huge amount of pixels, maybe 1 million, maybe more, I don't know. Okay, audio the same. Okay, we sample, audio at 44,000 hertz every second. So you can just imagine how many data do we receive. Okay, so we can maybe, every pixel that we observe, every image that we observe has some label. Okay, that's the information that we get from the training set. And so we can actually think about learning as a sort of a high-dimensional interpolation problem. Okay, so again, we can use an idea that is very cherished by mathematicians, applied mathematicians. Okay, so you have a function that you don't know. That's the function that solves your task. And you observe this function in some points that are given by your training set. The only difference, that is a key difference, is that in that space, the function lives in a huge dimensional space, okay? 1 million dimensions. It's not an interpolation of a 1D function that you can solve with splines or whatever. It's a huge dimensional interpolation problem. Okay, so of course, that's the goal of the game. You have a function that you don't know, that I printed here like with these very simple level lines, and you only know it here. Okay, so you have to go from here to here. Okay, so of course, this problem seems completely hopeless without assumptions. So if we have you know, a mathematical mindset, we can try to be very pessimist. Okay, so let's say, what is the weakest thing that we can assume? Okay, what is the weakest set of assumptions that we can use to go on, to continue? And something that was very influential, that really created a lot of sort of traction in the learning community, is to assume very little. And assume very little essentially means that you have to assume that the function f is smooth. Okay, the function that you want to estimate needs to be smooth. If it's not smooth, there's really no way you can you can transfer information from the training set towards the test set. Okay, you need some regularity, you need some smoothness. So how can you express this mathematically? Well, like a very weak form of smoothness is Lipschitz. Okay, but basically Lipschitz means that if I have 2 points that are close, the function needs to be close. And in a sense, this constant here is uniform. Okay, we have a constant that we can sort of compute as the supremum over some compact set there. Okay, so the question is, how many points do we need to observe? So how big needs the training set need to be? To guarantee is to have some sort of guarantee that our learning algorithm is going to succeed. Some ideas? Okay, if I want to make the error small, how many points do I need? In other words, what is the relationship between the size of the training set and this epsilon here? Some ideas? What?
Nyquist sampling of the manifold on which?
You have 2 things, right? You have error and you have dimension. You need an exponential number of points, right? And that you can think that you have a space, like that is like think that is a cube that has d dimensions. How many points do you need if you want to be sure that all your the training set is gonna cover this huge space at space that is a distance that is at least epsilon, so that you are going to be able to interpolate. You need an exponential number of points. Okay, and that's the course of dimensionality. It means that there's no way that we can brute force these problems. Okay, there's no way we are going to be able to collect, you know. Well, this is very scary. Okay, so you have something that has 1 million in the exponent. Forget about it. Okay, there's no way we are going to brute force these problems. So what does it mean? This? It means that if we want to advance in this problem, if you want to do machine learning with images, we need something else. We need some assumptions. We need something. Okay, we need to exploit that images are not just random points in this million-dimensional space. Okay, images have some structure, and so we can introduce this idea. We can try to learn through this idea of invariance. Okay, so we know that images have some symmetries, have some regularity. What do I mean by that? If I look at the supervised learning problem, I have a number of observed training points, and if I know that if I observe this little can here, this little thing, and the training set tells me that that's the label, that's how they call this? I don't know. I don't know how to call this. Cap. Okay, that's a cap. So if this is a cap, and I take this as a point in this high-dimensional space, if I move a little with my cap, or maybe if I flip it, or if I rotate it, it's still a cap, right? So whatever point I observed, okay, whatever function I'm trying to estimate, has some regularity, okay? That is just goes beyond this notion of Lipschitz, okay? So if I take my signal and I apply some deformation that we will specify later, the function is smooth in that direction, okay? And this is going to be our sort of line of survival, okay? We need to exploit this thing to be able to learn. And the same thing applies for unsupervised learning, okay? Unsupervised learning is considered to be like the next frontier in machine learning and deep learning. Same thing applies, okay? If you want to estimate the density in this huge dimensional space, it seems like a hopeless task, okay? It's just too big, the space. So we need to be able to exploit as many prior knowledge as we can, okay? So really, deep learning is nothing else than exploiting your priors, okay? There's a lot of prior information, okay? There's nothing that you can just learn without assuming anything, okay? In that case, the priors really come from math, actually, and from physics. Okay, so I told a lot of things already. Sorry about that. Let's try to summarize, okay? So what we are trying to answer is, how can we break the course of dimensionality when we have to deal with images and sounds? Okay, and Uriol, I think, is going to tell us about how to break the course of dimensionality when we have even more crazy stuff, okay? Text or whatever. Okay, and we said that we are going to try to take this perspective, that we are going to try to simplify our lives, okay? We are still going to work in some Euclidean space. Okay, we want to think about points. We want to do linear algebra. Okay, we want to be able to compute SVDs. We want to be able to estimate covariances. Okay, so we need a Euclidean space. Otherwise, I don't like it. Okay, so we are going to define a Euclidean a metric that is Euclidean in some embedded space. Okay, so we are going to put all the structure of the problem into this nonlinear feature representation. Okay, and we are going to try to see how can this be applied both for the supervised learning problem and perhaps, if we have time, talk about unsupervised learning. Okay, and so for that, we are going to see that we arrive pretty naturally into, by starting like doing step by step, we will end up pretty naturally with convolutional neural networks. Okay, so the convolutional neural networks is a very interesting and very powerful way to break this curse. Okay, and we are going to spend a lot of time here, and then I'm afraid we are not going to be able to describe this. We are just going to do some applications here, and we are going to end up with some open problems. Okay, so how do we start? Okay, so as I said, many of these tasks, it's not just about I give you an image and I give you additive Gaussian noise. That's very boring. Okay, so that's something that, again, beautiful theory, but it's essentially solved. Okay, we know how to solve the problem with additive Gaussian noise. For these problems that I described, the noise is much more violent. Okay, so think about another form of noise that rather than taking an image and adding, changing the pixel values with some random variable, we are going to add Gaussian noise, or we are going to add noise to the location of the pixel. Okay, not to the pixel value, but the location of the pixel. Okay, so what do we mean? We are going to move pixels around. Okay, and we are going to move pixels around. Why do we care about this model? Well, look at what we can model with that form of noise. Okay, so we can take this image here, and if we add noise to the location, we can warp images. Okay, we can deform images. Okay, and we can go from here to here to here to here. This is a form of noise that is much more appropriate. It's really nailing the variability that we have in these problems. Okay, if we want to do recognition, we need to be able to. Is this me? That is. Okay. Sorry about that. Okay, maybe I can do this. No, that's not good. Okay, sorry about that. Okay, so that's a form of noise that allows us to understand, to model mathematically that sort of variability. Okay, and so of course, again, if you think about how statisticians have been dealing with that form of noise, you need to, in a sense, come up with a notion of signal-to-noise ratio. Okay, that's the quantity that controls how hard is the problem, how good is our algorithm. So here again, we need to, in a sense, come up with a notion of how much noise do we add. What is the deformation cost? Okay, so here the noise comes into the form of deformation, okay, which is taking every pixel and sending it somewhere else. And so how much noise are we going to add? It's something that we can quantify with sort of a norm over diffeomorphisms. Okay, so we can, for example, pay a price every time we take a pixel and we move it far. Okay, that's this term here. But we can also pay a price that might be different if we take 2 pixels and we stretch or we contract. Okay, you agree with me that if I take this thing and I move all the pixels using the same displacement here, that moves things but doesn't stretch things. Okay? If I take 2 pixels and I start squeezing and stretching, that might really destroy the content of the images. Okay? So it makes sense to sort of take these 2 quantities and maybe have a nice trade-off. Okay? So that's the scale of the problem. And with this, we can actually model many things. We can model translation invariant. We can construct a translation invariant representation by asking that, essentially putting this scale to infinity. And we can model things in speech processing. Okay, so when we remember the first slide when we had these encyclopedias, okay, encyclopedias, male and female, essentially we can model it as a sort of a displacement in the time frequency domain. So how do we deal with this form of noise? Okay, we can start as many great mathematicians before us did. Let's try to answer this question in the linear world. Okay, what is the best linear operator that is consistent with this form of noise? Okay, so in other words, what is the best linear measurements that are going to be stable to that form of noise? So it's very easy to see that the only thing that we can do is to blur. Okay, blur is basically taking the image and convolving it with a low-pass kernel. Okay, that's the low-pass kernel here. And this operator is stable in the sense that if I have my image here x, and I compute the measurements a, that are the low-pass filter, if I had now an image that I deform, and I compute the same measurements, they are going to be close. And the distance between these measurements in the transform space is going to depend on how much deformation I have applied. So far so good. But what happens with these measurements? Can we do recognition with just these measurements? Well, I don't think so, right? I mean, if I take this input and I blur, I lost my ability to recognize things, right? Just these measurements, so I have stability, but I have lost discriminability. Okay, these measurements are not going to be sufficient to solve the problem. Okay, and this, I mean, Uriol that has been talking with deep learning people all the time, I mean, that would be completely obvious, right? No one does deep learning or machine learning with just linear transformations, right? Linear is a bit boring, and in a sense, we can see the limits of deep learning of linear operators here. Okay, so we need something nonlinear. So how can we have something that is a bit constructive that solves this problem? So in a sense, this low-pass filter, now we can take the perspective of harmonic analysis. It's a low-pass filter that sort of kills the high-frequency information. And this high-frequency information is key to recognition, right? We need this high-frequency information, okay? So how can we recover it? We can recover it with other filters that are going to be responsible for recovering this information that we have lost with a low-pass filter. And we can do that with filters that are maybe selective in different orientations. Okay, so that's think about when you have edges that depend on some angle, you want to have filters that are reactive to this direction, but not this one. Okay, and if you have a bunch of them, you can cover all the possible orientations. And the same thing, you can have filters that are selective at different scales. Okay, so this filter, it turns out that it's, again, something that we understand very well mathematically. We can design these filters such that the operator that takes x to all these measurements plus the low-pass filter is an operator that we can invert. We can understand its properties. And it turns out that there are many ways to extract this high-frequency information. Okay? And one way that is particularly interesting, and I'm not going to go into a lot of details here, is that we have seen that there's only one class of linear measurements that are invariant, that are locally invariant to deformations. Okay, so, and actually these are the only ones. So what is the next best thing that we can ask for linear measurements that is not invariance? So it turns out that something that is pretty interesting that we'll see that is really at the core of convolutional neural networks is the notion of covariance. Okay, so what we want is that, okay, the linear measurement is not going to kill the deformation, but at least it's going to commute nicely. Okay, it's not going to completely destroy the action of the deformation. It's going to create the notion of covariance. What do I mean by that? Is that I have these linear measurements here, and I apply them to something that has been deformed. I can approximate this action as first taking the linear measurements and then applying the deformation. Okay, and it turns out that this is really something that allows us to understand why convolutional neural networks work well, at least in that simplified setting. Okay, but as I said, these linear measurements are unstable, right? They are because that's what this result says. So I need to introduce the nonlinearity. Okay, I need to introduce a nonlinearity here. So what class of nonlinearities can I come up with to help me understand mathematically what's going on? So it turns out, again, that we can reduce this test to just searching for nonlinearities that are called pointwise. Okay, what does it mean, a pointwise nonlinearity? Is I have a function here that it can be, like, again, a super large image. And so a nonlinearity that is pointwise is not only going to act pixel by pixel independently. Okay, so it's just going to look at every pixel one at a time, and it's going to sort of come up with a proper way to sort of apply a nonlinearity at each pixel. And amongst all of them, so the reason why we can care just about pointwise is because, again, a pointwise nonlinearity, you can check this on the back of an envelope, is a nonlinearity that commutes with diffeomorphisms. Okay? If I apply a warping, a change of variables, like a deformation, and I apply a pointwise nonlinearity, that I'm not going to mess with pixels that are one talking to each other. Okay? So if every pixel only is transformed independently from the others, it means that if I move pixels and I apply the nonlinearity, it's the same as if first apply the nonlinearity and then I move pixels. Okay? That's pretty easy. And it turns out that it's only the only class that has this property. Okay, and now we are going to just take the modulus because I like modulus, okay, because it has this property that it preserves the energy. It's a nonlinearity that is unitary. But there are many other choices that also work well. Okay, so now we have 3 ingredients. I gave you 3 ingredients. Linear operator that is stable, linear operator that complements the low-pass filter, and pointwise nonlinearity. How can we take these 3 ingredients and construct a good signal representation that solves our problem? So we start with our signal f. We apply the stable low-pass measurements. Okay, we apply the blurring. That is going to give us good measurements. This information is lossy. We lose all the high frequencies. We're going to recover the high frequencies with a bunch of wavelet coefficients at every scale and orientation. Sorry about the noise. Up. Yeah, I don't know. Sorry about that. Okay, let's see. Okay. Does this work better? Okay. Okay, so I computed these wavelet coefficients, and now I have applied my pointwise nonlinearity. Okay, so I have a bunch of, so I had here one image, now I have a collection of images here. So what can we do with these images? Well, now these images have been transformed with this pointwise nonlinearity. So think about this pointwise nonlinearity as a sort of like demodulation. Okay, so when I take the modulus of a signal that oscillates, I'm killing the oscillation. Okay, so in a sense, you can think if here you have people doing EE or telecommunications, I guess that there are a lot of people. What happens when I take a signal that is bandpass and I kill the oscillations? What happens? No one? The energy moves to the baseband. Okay, so I have a function that doesn't oscillate anymore, or oscillates a bit less. So the energy goes back to the baseband. So what happens when I have information that now is in a baseband? It means that I can compute, I can extract energy, I can extract information with a low-pass filter again. Okay, so in a sense, I can repeat the process. I can take my machine and I can reapply it again. Okay, so I have this signal here, and now I extract the low-frequency information again. And what is the information that is lost by this convolution is carried by a new family of wavelet decompositions. Okay, and then I can take the nonlinearity and I can repeat this again and again and again. Okay, so what do I have here? I have a representation that is nonlinear. There's a lot of nonlinear stuff going on here, but so what are the operations that are involved? Convolutions, pointwise nonlinearities, and that's it, right? And I repeat this again and again. So this is a convolutional neural network. It's a very dull convolutional neural network because I didn't tell you there's no learning, right? Here, I just give you a family of wavelet coefficients that you have to organize somehow, and then you get information at every step. Okay, so what is the intuition of this? Representation? Okay, what is this telling us? So let's look at an example. Okay, so here we have a little patch. Think about this as a sort of a little portion of an image. 2 of them, right? There's one that looks a bit noisy. There's one that looks very geometrical. There's a triangle here. Okay, so the Fourier transform looks pretty different, but no one does Fourier transform to do image processing, image recognition. Okay, so one thing that people were doing a lot before ConvNet arrived is the SIFT transform. Okay, maybe Farhan knows about the SIFT transform. Yeah, I'm sure. So what is the SIFT transform? Okay, the SIFT transform is nonlinear feature extractor that what it's going to do is look at every patch and extract information at every scale and orientation, and then just look at the amplitude energy that I have along each of these subbands. So think about it as a sort of a histogram. Okay, so I just try to organize the energy that I have into different bins. And what is every bin? Is orientation and scale. Okay? So what do we have with this feature? So SIFT was used a lot until, let's say, 3-4 years ago to solve a variety of different tasks. For example, I could use this to register 2 images. I could use this to actually do recognition. Okay? But there's a little problem. If I look at the SIFT coefficients of these 2 patches, they are exactly the same. Okay, so I created these images so that the SIFT coefficients are exactly the same. Why is that? Okay, so these 2 things look super different to me, okay, but they have the same SIFT coefficients. Why is that? It's because, well, they have the same average energy along each scale and orientation. Okay, so the average energy is the same, but the way this energy is distributed in space is very different, right? And this is actually something that is completely essential to the recognition. So where is this information being captured? So this information is being captured in our second layer. Okay, so now we can interpret the shift as being the first layer of our transform, right? That's exactly what I told you. Wavelet coefficients, modulus, averaging. Okay, that's exactly the first layer. The information that is lost by this first layer, I told you that you can recover it with the second layer. And this here is something that really carries the geometric information. Okay, so this information is necessary. That's why you can use this to say deep is good. Okay, it's a bit hand wavy, but here you can really see the second layer in action, right? It's really recovering geometric information that is very important. Okay, a slide of math. What can we say about this representation? We can say very precise things. Okay, we can say that it's stable with respect to additive noise, the noise that it's a bit boring, okay, but we still need to have it. And it's also stable to the geometric noise that I described. Okay, and there's a little animation that shows you what's going on. You have a little high frequency patch that I'm starting to dilate and deform in a very nasty way. If I try to understand this using classical tools like spectral analysis, if I look at the the spectral density of this little image that is being dilated, you see that the frequencies, the energy is really jumping all over the place, right? The high frequencies are very unstable. If I look at the spectrum in my new nonlinear representation, everything is in place, right? There's some movement, but most of the energy stays in the same place. Okay, so this is very important if I want to do classification, right? Because these two things are essentially the same, right? If I dilate, it doesn't really change our perceptual quality. Any questions? You look like a very silent audience to me.
Yeah.
Okay. Okay, good. Okay, let's move on. I told you about how can you construct a representation that is placed well with deformations. So now I give you these images here. Okay, so you have some stone, some whatever. Everyone is able to tell me that these things are the same, right? And these things are the same class, and these things are the same class. But do you think that it's the best way to start looking at what is the deformation that moves one stone to the other? What is the sort of the rotation that goes from one to the other? Doesn't seem right? The model here is not the same geometrical model. Okay, so here the right way to think about this problem is that these things are realizations of a stochastic process. Okay, so these are, in a sense, there's an entity that is a statistic entity, like a process, that produces samples. Okay, and these samples are stationary. Okay, so in other words, the statistics in this part of the image are the same as the statistics in this part of the image. And typically we are non-Gaussian. Okay, so forget about your, I'm sorry, again, I don't know if you thought this, but forget about ARMA and Gaussian processes. Okay, nature is non-Gaussian. Okay, it doesn't work. Okay, if we just think about estimating the power density, we are not going to be able to do it. Okay, so here, what is the right way to think about this problem? We have, again, the goal of the game is to find a representation, now not just of an image, but of a process. Okay, so that's the underlying thing that we want to be able to classify. We want to represent this as a whole, right? We want to have a process that we want to compare to another process. Okay, that's what classification in textures asks us to do. But of course, we don't have the process. We don't observe X. Okay, we only observe samples of X. Okay, so we represent the process with a bunch of nonlinear moments, but we are only going to be able to estimate this process by basically replacing the expected value by the empirical average. Okay, we are able to average in space because what we are assuming here is that the process is stationary. Stationary means that we are allowed to average in space or in time. Okay, if we are working with time series. And so I told you a lot of things about the importance of being stable, right? We want to be able to play well with the deformation before. So what is the notion of stability here? The notion of stability now is a statistical notion. Okay, so we want our estimates to have low sample variance. Okay, so we want the variance of our estimator to be small. Why is that? Well, if you have an estimator that has very good theoretical properties, but if I give you data, it behaves crazy. Okay. If you know someone who works in a hedge fund or does finance, he's gonna laugh, right? Okay, you can theoretically do crazy things, but if I give you data, it's gonna behave like crazy, right? It's gonna have huge variance. Don't take it, right? So here's the same thing. Okay, the variance of the estimator is very important. And so here these are again our two things that are in tension. We want to have representations that are good at separating things, but that are stable, okay, that have low variance. So how can we do that? not very original. So we have our process here. And now we replace our linear operator before by the expected value. The expected value is a linear operator in processes. Okay, just taking the first moment. What is lost by the first moment? All the increments. Okay, all the increments of the process are lost by the expected value. So you take the increments at every scale and orientation. And what do? We kill the phase. Okay, so we do the same thing. And now we have a process here. What is the expected value of this process? Is it 0? No, right? Because I have killed the oscillations. It's non-zero. So what I do is that I compute this first moment. Okay, so it's the same picture as before. The only thing that I do is I replace the linear operator that gives me stability with the linear operator on processes that gives me stability. So it's the same thing as before. Okay, so here if you have done some work on basically stochastic processes, but you will see that I'm defining a collection of moments that looks a bit different from the way people typically compute moments, right? Typically, you just compute the covariance, that's the second order moments, and maybe if you want to go fancy, you compute the higher order moments, which are polynomial moments. Okay? We take the moments of order 3, 4, 5, whatever. Here we are doing something very different, right? We are taking nonlinear moments. We're taking moments of these nonlinear functions of the process. Why do we do that? Why wouldn't we just stick with standard ways of estimating densities? Let's look at this in a second. Okay? So again, what is the intuition of these coefficients? Here we have two different textures. If I look at the power spectrum, they are exactly the same. Okay? So what it means is that they have exactly the same covariance structure. But then they look very different. So if I look at the first layer of my scattering network, what I get is that they are very close, right? Very hard to tell them apart. But these things are very different, right? They have the same second order moments, but the behavior in the high order moment is very different. Okay? So it's very, very different. And what is this difference being extracted? What is this difference being present? It's present already in the second layer of the transform. Okay? So if I look at the second layer of the transform, I can see that higher order moment has traces in that layer. Why is that? Some ideas. You cannot answer because you know. Why is that? Okay? What happens when I take a nonlinear function? What can I do with a nonlinear function? You have done this in analysis all the time. No? It's an English guy, I think. Taylor, right? If you do Taylor, okay, you can express a nonlinearity as a series of polynomials, right? So every time we do a nonlinearity, we are, in a sense, indirectly computing higher order moments. And the more nonlinearities that we do, the more nonlinear moments we are, in a sense, putting into the mix. Okay, so in that case, cascading nonlinearities is good, right? Because it gives us, in a sense, it creates a dependency of our features with respect to higher order moments. And higher order moments are very important to do classification. Okay? So of course, we are extracting higher order moments, but we are not doing it directly. We are doing it through this fancy, convolutional neural network. Why is that? Sorry about the second. There's another math slide here. The reason why we do that is because we want to have consistency, right? We want to be able to have estimators that have variance that is controlled and goes to 0. Okay? And this is something that is not possible if you just estimate the higher order moments directly. Okay? And so I'm not going to go into the details. If you're interested, you can talk to me. But the bottom line is that if I extract information using contractive operators and I cascade them all the time, I get access. Okay, I have estimators here whose variance, okay, that's the variance of the estimator, goes to 0, okay, as the number of samples increases. Okay, and it goes to 0 at a good rate. Okay, the constant here is important. The constant that I see here is just something that essentially depends on the second order moment of the process. Okay, if I want to estimate the third order moment of a process, and I do it with a sample third order moment, I will see that the constant depends on the moment of order 6 of the process. And this can completely kill you. Okay, if you have a process that is non-Gaussian, you are dead. Okay, and so we are able to estimate higher order moments with a constant that is not depending on higher order moments. Okay, and here again, this result holds if we are able to keep on adding layers. Okay, and we add layers, and the rate in which we add layers is actually logarithmic with n. Okay, I'm going to go very fast across this because I have things to tell. Sorry. Okay. Okay, so one of the questions that we can ask is, what are the sort of the recovery properties of these features? Okay, so here we have extracted nonlinear features, okay, and we can construct many of them by adding layers. And so one natural question is, are we losing information? Okay, is this representation complete? Okay, we are doing something nonlinear. Is it throwing information? If we do this in the sort of stochastic case, we are computing a bunch of moments. What is the process? Okay, what is the distribution that is characterized, that is contained in these moments? Okay, so this is a very natural question. It's a bit more something that is more interesting to maybe someone who is more theoretically minded than someone who is more like a practitioner. Okay, but these are still very important questions. Okay, so this is just to give you a glimpse of what are the results or what are the things that we are able to say by adding an auth structure into the convnet, right? Adding an auth structure. So here we have a very simple result that says that if I have a process that is very sparse, okay, so what this means, sparse, think about a process that has lots of zeros, okay? So in image, if you look at the, let's say the Laplacian, like the gradients of the image, they are very sparse, okay? If you look at the time series, you can do some transformation that makes it sparse. Okay, so if I have a time series that is very sparse, I can express it as a sort of a point process, and I have some, let's say, sufficient, like a very weak assumption. It means that the spikes are separated by some minimum amount of like separation. What it means is that this scattering representation that I obtain is essentially characterizing this class of point processes. Okay, so what do I mean by that? Is that if I have another signal that has the same features, it's necessarily a point process. Okay, it's a sparse thing, and the separation, the scale in which this point process lives, the separation between the spikes is the same up to a log term. Okay, so just to give you the high-level idea, what this means is that these features, okay, are characterizing sparsity, okay, in a very stable way. What do I mean by that? Is that we don't have exact recovery. Okay, that would be completely crazy. Why is that? Because the number of features that we have in the first layer, remember, is indexed by the number of scales. Okay, so the number of scales, if I have n pixels, is log of n. Okay, so I have a representation that is it has a very, very small number of features with respect to the input dimensionality. And so, of course, we cannot recover the exact signal, but we are going to recover something that is close enough in a geometric sense. And this result can be extended also in the several dimensions. Okay, so here I told you what happens in 1D, but you can do the same thing in 2D. What else? Another thing that we can recover with the same thing is signals that are very sparse, not just in space, but also in frequency. Okay, so these are things that are sort of like waves. Okay, so let's say that I have a signal that oscillates at resonates at a couple of frequencies. Okay, so it's something that if I look at the Fourier transform, is very sparse. So the same thing holds. Okay, so the same features, exactly the same features, are good at recovering this class of very sparse processes in Fourier. Okay, and so think about these features that are based on this multi-resolution filter, that are the wavelets, somehow sit in between things that are very sparse in space or things that are very sparse in Fourier. Okay, they're somewhere in between. And we get something that is like a good compromise between these two classes of very, very sparse, sort of what I call like extremal solutions. Okay, so let's see some numerical experiments. It will become more clear in a minute. And so how are we going to be able to test this recovery? Okay, so here, remember the goal of the game is I have this signal, I compute these features, and now I ask the question, can I go back? Okay, can I invert this representation to understand what's going on, to understand what is lost, what is kept? So how can I do that? I can try to find like an input x such that its scattering coefficients match some coefficients that I have previously computed. The way I solve it is by trying to solve this nonlinear least squares problem. Okay, so this is a problem that is a bit nasty. I don't know if you people here do optimization. This is a non-convex optimization problem. The way we solve it, very naive. We just do gradient descent. Okay, so we do gradient descent, and actually, even though it's a complicated non-convex problem, we can have some very weak notion of convergence. Okay, so with this algorithm, we can show that under some very nice conditions, it doesn't stop. Okay, it succeeds. Okay, it can go arbitrarily slow, but it always lands into this sort of manifold that satisfies our constraints. Okay, so let's see some examples that hopefully will make this clear. Okay, so here we have a very simple class of images, n square pixels. Let's see what happens if we try to reconstruct by using only one layer of the transform. Okay, so how many coefficients do we have? We have log n coefficients. Okay, that corresponds to the number of scales that we are extracting. Okay, log n coefficients. As you can see, things are not very great, right? Doesn't really solve the problem. What happens if we add 2 layers? Okay, we have log n squared coefficients. We are still in a very compressive regime. Okay, log n squared coefficients. What you can see is that suddenly the geometry emerges, right? We are able to essentially reconstruct something that has the same, that looks the same. Okay, if you computed the L2 distance between what we recover and what we have, it would be very bad. Okay, but that's not the point. Okay, the point is that these coefficients are very compressive. Okay, log n squared, and capture something that is quite essential. Okay, and this is something that is, in a sense, explaining the performance of these networks, as you will see, in classification problems. The same thing, we can do it for the textures. Okay, so we can have here a bunch of textures. That's the reconstruction. If you just use the Gaussian theory, just try to estimate the covariance and try to reconstruct a Gaussian process that has the same covariance structure. Well, it doesn't look very great, right? Again, if we use these coefficients that are very small, log n squared, as you can see, the results are not perfect. Okay, so these things look a bit crap. Don't look so perfect. But there's something quite essential that is being captured by these coefficients. Okay, so we have a very, very small number of coefficients. And remember, log n should sound good to you, right? I told you before that what is the dependency of my sample complexity with the dimension is exponential, right? So exponentials and logs break the curse of dimensionality. Okay, so something that compresses into the logarithmic dimensionality space and still is able to contain something that is pretty essential is a good idea. Okay? Okay, what can we do with this in practice? Well, we can do simple things. Okay, so we can use this to classify pattern recognition. We can do this to do texture classification. We can do this to do object recognition, I would say small scale. And so here we get state of the art. Okay, so we get good results that are on par with the best methods, at least when they were published. Okay, now I think that there's crazy people trying to squeeze this set, but don't believe MNIST. Okay, so if just an advice, if you are working now on pattern recognition, please don't use MNIST more than 30 minutes. Okay, so we are reviewing, Oriol and me, we are reviewers. We see a lot of papers that tell us, oh, I have this wonderful method, it works well on MNIST. Yeah, but even if you do like random things, they work pretty well in MNIST. So please don't do that. Okay, it's an advice. Okay, so on mid-scale auto recognition, we get, by sort of optimizing the wavelets, we get about 17% error. Okay, so 70% error, you might wonder, is it a good number or not? Well, if that was done 5 years ago, that would have been awesome, right? Like, wow, state of the art. But now, the error is at about 5%. Okay? So how good is 17% with respect to 5%? It's not good enough, right? There's something, it's not a detail. It's not just, that I was not tweaking enough, or, that I could have spent like an extra weekend tweaking my parameters. There's something fundamental that is missing. Okay, so with everything I told you so far, we can do some mileage. Okay, we can understand this problem. We can understand this problem. We can do a little bit of this problem, but it's not good enough. Okay, what is missing? Well, what is missing is that we are not learning, right? We are just, I'm giving you this multi-scale transform, this wavelet, that plays well with this model of variability that is deformations. But real images have deformations, we agree, but they have many other things. I told you that, crazy object recognition, if I have to recognize bottles of water, okay, there's a bottle of water, but I don't know, if I go to Brazil, the design might be super different, right? And I cannot maybe understand one from the other with a deformation. There's something that really needs to be coming. We need to extract more from the data, okay? And so this is where ConvNets come into play and really shine. Okay, so what is a ConvNet? For those of you who are not familiar, it's essentially what I described, but convolutions here, you replace the convolutions with generic filters, and also something important, at every layer, you are not just taking your image and completing a filter on that particular image. You can take the whole stack of images, okay? So it's like a channel, think about this like a multispectral image, and you apply a convolution, a generic convolution, okay, which is like convolutional tensor. So you recombine the channels together. Okay, so you recombine the channels, and it turns out that you can recombine the channels to really boost the discriminability of the model without compromising the stability. Okay, and so it turns out that if you apply these things on like object recognition, what you get in the first layer, okay, so it looks good, right? I mean, our theory is not, you cannot just throw it into the bin. What I told you before, you can use it to understand things, right? Because if you look at what happens in the first layer, what you get are things that look a little bit like wavelets, okay? And actually, this is not new. I mean, people in neuroscience have discovered the same first layer structure in the monkey. They have found it. You know, there are numerous evidence that shows that this is a good first layer. Okay, we have a good picture of what happens in the first layer. After that, here, much less clear. Okay, and so just a bit of history of ConvNets, and I will conclude in 5 minutes. So where do ConvNets come from? So ConvNets come from neuroscience. Okay, so actually, I think that these two guys got the Nobel Prize. Okay, Howard and Whistle, and they were trying to understand things like they were experimentalists, right? They were getting their hands dirty. Okay, and they came up with a model that could explain what was happening in the visual cortex by this idea that you have several stages of computation that look a little bit the same. Okay, by repeating something simple, you can get to something that is very rich and very expressive. And then there was this crazy Japanese guy, Fukushima, who came up with a model that could be used in machine learning. Okay, so he said, well, if this is something that works, that we experimentally found in visual cortex, why couldn't we use it in our computers? Okay, so he came up with this neocognitron, but except that there was a little problem that he didn't know how to train it. Okay, he had this very nice architecture. He got the good architecture, but didn't have the good training algorithm. So who got the right architecture and the good training algorithm? Jan. Okay, so Jan really put 2 and 2 together, okay? And boom, he was, in a sense, he was able, the first one who was able to show that, yeah, I mean, you get something that is good, that plays well with the physics. And now he came up with a good algorithm, and the good algorithm is nothing else than the chain rule. Okay, we all knew it from before. But it's not because it's easy that it's not interesting, right? I mean, if that was so easy, why didn't Fukushima have this idea? Who knows? Okay? And so he was using it in AT&T, really deployed in production. So it's not just, it's very important to say this, right? It's not just something that you do in your lab, in the university, write a paper, that's it. No. This was it was used in the banks, right? To read checks. And I don't know how many checks they were reading all the time. So it's really, I mean, I'm not sure, well, Uriel will tell us more about how ConvNets are applied in practice. But this is really remarkable for me. Okay, so it was really used in production and with the technology of 20 years ago. Okay, so what happened? Something else happened. Okay, so these models have been around, I told you, 80s and 90s. People were, yeah, they were aware of them, but it looked like a black box. It looked like something very hard to use and manipulate. Until another couple of crazy guys like 3 crazy guys from Toronto spent 3 weeks or 4 weeks or I don't know how many months really doing the extra step, the extra leap that was necessary. Okay, so not just having the right algorithm, not just having the right architecture, but also the right resilience and the skills to really scale this thing up, to adding more layers, coming up with new tricks to train them, and look what happened. That's the ImageNet challenge. Okay, that's maybe the most important challenge in computer vision. They came up with an error that completely destroyed the competition. Okay, so that's non-CNN was like widespread in 2012. look at what happened. In 2 years, there's no alternative, right? It really completely destroyed and changed the field forever. Okay? And in speech processing, I think something similar happened. Maybe Uriol will be able to tell you more. He was working on that. So it really changed these things. And so not only we use ConvNets for solving image recognition, we can now sort of use it as a very generic toolkit for solving anything that involves images, right? Localization, segmentation, not only images. You can use it to understand things about molecular structure. Okay, molecules live in 3D. You have this idea that maybe if I have a molecule and I apply a small deformation, maybe the properties of the molecule are not going to change. So we have this prior. It plays well with our prior. So therefore, ConvNets should be a good tool to this. So here's another piece of advice. If you are working with data and your data lives in some low-dimensional space, so it's indexed by in low-dimensional space, so like images, molecules, whatever thing you are doing, and you can tell me that the data plays well with some physics, in a sense that if I apply a change of variables, if I move a little bit my data, if I rotate a little bit my data, if I deform a little bit my data, your quantity that you want to estimate is going to play well, it's going to be stable. I can sort of bet that a ConvNet is going to really do the best you can do. Okay, so that's, and then something that I really like, it's one of my fellows from Berkeley, Efros and his student, in painting. Thing that is completely crazy, right? I have an image, I block the center, and by using these ideas and many, many other things that I don't have time to describe, you are able to feel something, and this is really superhuman, right? A human would not be able to do that, okay? Think about it. You have an image, try to do it at home, right? You have an image, you block the center, and now you try to paint what is missing. Wow, it's completely mind-blowing to me. The thing I told you before we told that log n, we liked it because it was good, it played well with the math and the statistics, breaking the course of dimensionality. Well, we are also computer scientists, so we can also try to, forget for a second that we want to be consistent and see what happens if we boost the number of features. So we can replace the scattering by a very more modern, more fancy ConvNet and see what happens. Well, the same algorithm I described essentially allows you to synthesize textures that are completely crazy, completely mind-blowing. Look at that. That's synthesized. Okay? So I observe this thing, and now I can construct landscapes, right? It's completely crazy. You are able to synthesize a landscape. You are able to synthesize meat. Okay? So this meat doesn't exist, right? It's really something that is captured by the statistics that the ConvNet is able to extract from the data are really nailing the geometry. Okay, so it's really nailing what's coming on. Okay, you can use it to have fun, to do art. Probably you have seen this in the news as well. Okay, you can take a picture, you can take a painting, and you can combine them. How do you do that with a ConvNet? Okay, the ConvNet is able to, in a sense, disentangle the texture from the content. Probably you know this guy. So we use this guy to define the logo, and that's, I think, how I'm going to end. That's something that we organized last week. Okay, we just came here. Uriol was one of the speakers, and I really encourage you that if you like the thing that I talked about, video lectures are available. So please have fun. And so with this, I'm going to just conclude. Okay, so what I try to tell you with the time that I had here is that ConvNets are really here to stay because they are really breaking the course of dimensionality. Okay, there's something quite fundamental in these tasks that require to build some form of stability with respect to this class of deformations, and we are able to do that with basically by taking this very simple operation, and we need to repeat it. Okay, we need to cascade it. Okay, there's no linear transformation that can do that for us, and we can use it to solve both supervised and unsupervised learning problems. I didn't have time to describe applications in inverse problems. Uriol is going to tell you more applications, very cool applications. But what I also wanted to tell you is that it's not just an empirical field. Okay, so there are many, many open questions, and I really encourage, if you are here, mathematicians around, people who have been fascinated with, signal processing. It's really an open field, and it's really the best time to work on that. Okay, there are many things that we don't understand. How can you understand mathematically what's going on in the higher layers? How can you understand the optimization problem? Optimization is really, really something that is quite miraculous right now, and we don't really understand it. How can you extend these properties in non-Euclidean domains? Okay, so everything I told you was how to understand images and time series. What if I have, I don't know, a mesh in a 3D mesh, right? Can I do the same thing? Perhaps. So all these are open questions. And so with that, thank you very much. And maybe time for questions or, yeah.